Hi everyone, we are Senior Design Team, JuiceBox. Our members are Will Bowers, Graham Bruski, Jackson Meier, Jason Rico, and Maxwell Helton. Team JuiceBox was tasked with designing a battery management system for an electric vehicle for the Formula Society of Automotive Engineers competition, FSAE for short. The FSAE competition is a college-level automotive challenge for electric vehicles. Our system will ensure that the electric vehicle's accumulator will properly function as per FSAE rules to keep our drivers safe. This includes monitoring the battery voltages and temperature readings through the Orion BMS. The BMS is equipped with 3 voltage taps that are connected to each module's positive terminal with negative references every 12 modules. This system can monitor up to 90 battery modules. Here, we are only showing 5 without any load. The Orion BMS GUI is extremely vital to our project, as it allows for interpretation of the data that the BMS measures, both temperature and voltage. The GUI allows the user to define system safety parameters. One of these being, if the battery gets too hot and shows sign of thermal runaway, the Orion BMS will shut down any and all output of the system, thus sending an error code to the VCU so that the batteries will not discharge or charge. The voltages of the batteries need to be closely monitored because not only are they being used to power the car, but lithium-ion batteries are well known to parasitically drain each other. The Orion BMS GUI has built-in safety parameters that the user can input to dictate when a battery is too low or too high of a voltage to operate. After confirming voltage readings, we can collect temperature data. For temperature, the batteries themselves are equipped with thermistor circuits to record temperature data. The temperatures proved to be very challenging to obtain, as a lot of the circuitry for the batteries were hidden by the battery company. However, through some engineering, we were able to calibrate the BMS to gather data in accordance with FSAE rules. Here we are showing what it looks like when the temperature sensors are plugged into the batteries using a heat gun to simulate temperature changes. Finally, after we test, we need a method to charge the lithium-ion batteries. We resorted to using a standard wall outlet charger, but stripped and modified the cord so that it could charge one of the lithium-ion battery modules. For the future teams that come to take on this project, there is a plethora of tasks that need to be done in order for the entire BMS to comply with FSAE guidelines. This will include further safety equipment and implementation highlighted in our documentation. Here is a demonstration of our project. First order of business with this is connecting the individual batteries in a safe manner using proper safety equipment. As you can see, they are connecting the battery segments in series, prioritizing that there are no potential arcs, as it is extremely important to not accidentally close the batteries on themselves. If safety procedures are not followed, it can cause the circuit to heat up very fast, even with only 2 batteries. Improper safety procedures can result in severe burns, severe shocks, or loss of function of the system. One important thing to note is that we screwed in each row of the batteries first before connecting them to prevent potential shorts. Here we see Jay trying to demonstrate an accidental short, but the battery rows are not connected yet, so the system is a lot safer. Here we see the final configuration of the battery modules, power resistors, which are serving as the load, and voltage taps. Finally, we see Jay connecting the circuit together. And last but not least, we are showing what the live voltage data collection looks like while the system is under load. And finally, the students disassembling the project.